All right, let's talk product properties of exponents today. Basically, just remember, anytime you see the word product in math, you're thinking of multiplication. So all of these properties are going to have to do with multiplying powers together and what we can do with the exponent as a shortcut. So simplify, there's two meanings of simplify that we need to keep in mind throughout this unit. One of them means that the same base does not appear more than once. So in our example on the left here, the good example, we see that the bases are x, y, and z, and we notice that they appear only one time. There aren't two different powers with x, two different powers with y or z, for example. In our non-example, we see that m appears twice as a base, so that technically is not simplified yet. And through the course of this unit, we'll learn how to simplify something like that. The second thing that simplify means with exponents is that you can only have positive exponents. If you have any negative exponents, the expression is not simplified, and there's something more that we need to do. So an example, we have positive exponents on x, y, and z. In the non-example, we have negative exponents on x and z, where we would have to do something to turn those into positive exponents. So that's just something to keep in mind as we look at simplifying our expressions using the product properties today. Just remembering that in our answer, we have to make sure that the same base does not appear more than once and that you have positive exponents only. All right, so our first of three different product properties is called the product of powers. And the product of powers says that you can multiply powers with the same base by adding their exponents. Now, in algebraic terms, we can see here on our little formula, a to the m times a to the n. Now, notice that we have the exact same base on these two different powers that are being multiplied. A is being raised to the power of m, and it's being multiplied by a raised to the power of n. Now, if and only if you have those conditions met, that you're multiplying powers with the exact same base, a little shortcut is that we can actually just add the exponents together. I know that seems weird, like why, when you're multiplying powers, why don't you multiply the exponents? Well, that's not how it works. You add the exponents instead. And here's the why. Down below, I have an example where we have c raised to the second power times c raised to the fifth power. Now, if you expand these two expressions, so c squared is c times c, and then c to the fifth power would be c times c times c times c times c. Keeping in mind the exponent tells you how many of those bases are multiplied repeatedly. And now if I want to write that expression using exponents, I just count how many c's are in that list. 1, 2, 3, 4, 5, 6, 7. So my final answer should be c raised to the seventh power because I multiplied a c times itself 7 times. So for my shortcut, we're noticing that the exponent tells me how many of those c's are being multiplied together. So to count a total number of those factors just means to add the exponents. 2 plus 5 is 7, so it's c to the seventh power. So let's apply that here with our example number 1, d to the fifth power times d to the 12th power. I could write that out if I wanted to, expand it like d times d times d times d times d, but I don't really want to write all of that because it sounds like a lot of work. Instead, I'm reminded that the product of powers property tells me I just have to add the exponents 5 and 12, and that will tell me that my final answer should be d to the 17th power. In example 2, same thing. We're multiplying some p's together with more p's. So really, I just have to figure out how many total p's are being multiplied together. And my answer will be when I add the exponents. 31 plus 14 is 45. So it's p to the 45th power. Now, the power of a product property is a little bit different. This time what we're doing is we're raising a product, like something that's already being multiplied together, to the same power. So here we have an example where it's AB, which remember is A times B, being raised to the power of M. So what we do is we say, okay, if it's A times B, all grouped together in parentheses raised to the power of M, that's the same as taking the first factor, so a raised to the power of m, times b raised to the power of m. I like to think of this one as kind of like the distributive property of exponents. I have to distribute the exponent to all of the factors that were being grouped together and raised to that power. So in our example down below, how does this work? If I'm taking 3h and squaring it, that means that I'm multiplying 3h times 3h, right? I take that thing and write it twice because the exponent was 2. Now, if I rearrange these and kind of regroup, I have a 3 times a 3 and an h times an h, because each one of those represented just, 3 times h in the parentheses. So I'm just regrouping my multiplications. And then when I group those together, 3 times 3 is 9, and h times h is h squared. It becomes 9h squared, or 9 times h squared. Let's look at a few more examples of this property. In number 3, we have xy is grouped together in the parentheses, raised to the 7th power. So it's like multiplying xy times xy, basically 7 times. And in the end, you're going to end up with x times y, where each factor gets raised to the 7th power. So x to the 7th power times y to the 7th power. In number 4, we have 5w grouped together, raised to the negative 3rd power. So the first thing I want to do is recognize that the 5 times the w, I can split that into 2 factors and distribute my exponent. I raise each part to the negative 3rd power. Now, the problem with that is I have negative exponents. Remember in the first screen, we said you can never have negative exponents in your final simplified answer. So we apply what we learned about negative exponents the other day. I can take anything and turn it into a fraction. So there's my fraction bar and my 1. And anytime I have a negative exponent, I need to take that power, whatever that is, and I want to move it across the fraction bar. In this case, I'm moving everything to the bottom, to the denominator. So it becomes 5 to the positive 3rd power and w to the positive 3rd power in the denominator. Now, in terms of what's left over, if I moved everything out of the numerator, there's still that invisible 1 left behind. And then the invisible 1 that was on the denominator is no longer needed because there's other stuff there. The last thing I would want to do here is simplify that, the power that we can. 5 to the 3rd power is 125. So I'd write this as 1 over 125 times w to the 3rd power. That would be my simplified form for number 4. All right, our third property is called the power of a power property. So the power of a power is exactly what it sounds like. You are taking something that is already a power with an exponent and raising it to another power. In other words, a raised to the mth power is being raised to the nth power again. And the little trick here is that we can actually just multiply the 2 exponents together to get the new exponent. When you look at our example, a to the 3rd power raised to the 4th power is a to the 12th power, since 3 times 4 is 12. Now, why does this work? If we actually take a look at that expression and expand on it, my 4 as the exponent on the outside indicates that I'm multiplying a to the 3rd power by itself 4 times because the exponent was 4. Now, each one of those a's, or a to the 3rd power, excuse me, can be simplified even further to become a times a times a. So if I do that for each one, think about how many of the a's are being multiplied together as I write them out. So in the grand scheme of things, I had 4 groups, and in each group it was a times a times a. So altogether it's a to the 12th power because there were 12 of the a's being multiplied together. So that is the exact reason why this power of a power property allows us to just multiply the exponent. So just think of it this way. If there's two exponents right next to each other like that, just multiply them like you would any other number separated by parentheses. So let's look at a few examples to practice this. Number 5, we have x to the 4th power squared. Well, let's see. I've got two exponents right next to each other. So I know that I can just multiply my two exponents. And this becomes x to the 8th power. Kind of see it worked out the long way using our exponents and expanding. Okay, I'm expanding that there's x to the 4th power multiplied twice. So there's my use of that exponent. And then I can think of that as, oh yeah, I had a property earlier where we did this. X to one power times x to another power. I add the exponents when I see it like that. And in the end, I still get x to the 8th power. For number 6, b to the 3rd power raised to the 7th power again. I see that I have my two exponents right next to each other. So I'm reminded that my property says I can just multiply the two exponents to get my new exponent. It should be b to the 21st power. All right, let's look at just a few more examples where we are combining some of these properties together to simplify the expression. In number 7, I see that I have a 2 and y to the negative 6th power that's then being raised to the 2nd power. So I have two factors inside the parentheses being raised to the same exponent. So the first thing I'm going to do is distribute the exponent. So I'm going to have 2 raised to the 2nd power, and then I'm going to have y to the negative 6th power raised to the 2nd power. So I distributed the exponent of 2. Notice when I had something that was already a power and I'm raising it to another power, I use those parentheses to group that together to show that I'm only raising the y to the negative 6th power, again, to the 2nd power. So let's simplify even further. Well, 2 squared is just 4. And when I simplify the y's, I'm reminded that I should multiply my exponents. Negative 6 times 2 is negative 12. So it becomes 4 times y to the negative 12th power. Now, I can't say that's my final answer yet because it's got a negative exponent. So we have to take anything that has a negative exponent, just that part, just the y's, move it across the fraction bar. So I'm going to move it down to the denominator, and it's going to become 4 over y to the positive 12th power. All right, with number 8, we get to see a little bit more use of that first property with some of the others as well. First thing I want to do is start by simplifying with that 4. I have a factor of m squared and another factor of n cubed that needs to be raised to the 4th power. So I'm going to start by distributing my exponents, and that's going to leave me with, let's see, m squared is raised to the 4th power, and then the n cubed is also being raised to the 4th power, and then I still had that n squared at the end. I don't want to lose track of that. Okay, so I have to just add that in, or include that. Sorry, there's no adding. Now I want to start simplifying. I have m squared to the 4th power. That's my power of a power rule. So I want to multiply my exponents there. That's going to give me m to the 8th power. Then I see I have n to the 3rd power raised to the 4th power. Again, I want to multiply my exponents. 3 times 4 is 12. And let's see, we've got positive exponents. But I've got n's and more n's. I have 2 different powers with n, the same base. So I'm not done simplifying yet. I want to take those 2 and combine them together. So think about what property would we use to combine the n's? Or when in doubt, write it out. What would that look like if we wrote all of those m's and n's expanded? I would have, well, m multiplied by itself 8 times, so I'll leave that the same. But all of the n's, think about how many n's would be in that list. N times n times n times n times n times n times n, and so on. A total of n to the 14th power, because we add the exponents to find a total number of n's that were used as a factor. M to the 8th power times n to the 14th power.